Oh. Yeah, as you can see, this paper is about trees in the biological sense, although I promise that graphs will play a role. All right, so for the beginning, I want to talk a little bit how trees for real-time media are typically generated, because artists don't place individual leaves on trees usually. They instead design parameters for procedural tools like SpeedTree, Houdini, or Blender, and then these tools generate the trees, and then for rendering in a video game, you would export them to a polygon format in typically different levels of detail, and then the engine selects a fitting level of detail for the current frame and renders it. Now, this process comes with a couple of problems. You want very detailed trees nowadays, and they can sum to very large amounts of memory, so you would need to have a very high memory demand. So one thing you could do to mitigate this is maybe real-time decompression, and there's ways to do that, but you would probably only get like compression by a factor of 2.5 or something, so that doesn't really solve the problem. Next problem I want to mention is that the geometry is typically static, but you would want to like have the trees sway in the wind, and one way you could do this is with rigging, and this is a scene from Alan Wake 2, where they have a forest scene, and they report for this scene they have 300,000 bones. So you can imagine this probably requires a lot of engineering to get this running in real time. So that's also complicated. Next issue I want to mention is with the discrete level of detail system. So when you change level of detail, you usually would see some kind of popping artifact, and you don't want that. One way to solve that could be maybe tessellation. So you have an example from Star Wars Battlefront, and they use tessellation when you get close to the trees. They displace the geometry a little bit to add more detail, and they can do this smoothly, but for like the lower level of details, this is not really possible. So this is limited to higher level of details. And the last problem I want to mention is that with slow generation, so these generation problems that I mentioned, they take anywhere from a minute to hours to generate trees. This lowers the artist productivity because designing the parameters takes a lot of time. And to fix this, last year I presented a paper about real-time procedure generation with GPU work graphs, where we generate everything, every frame, and you can see changes of the generation parameters immediately. And this year, I want to do something similar. I want to have parameters that feed into a work graph, and this work graph renders trees to the screen, and this work graph should solve all these problems that I've mentioned. Okay, let's do a quick recap on GPU work graphs, and we want to render a tree. So we have a node of a work graph, it's called tree, and a node of a work graph is just a compute shader. And this compute shader receives as input a line, and this line is just a struct with 2 points. And the tree node also has an output to another node, a mesh node, the line mesh node, which is for drawing that line. And the mesh node is a fairly new feature of work graphs. It consists of a mesh shader and a pixel shader. And when we code that out and dispatch a work item to the line mesh node, we can draw the trunk of our tree. Now, this is a fairly boring tree, so let's make it a little more complicated. Let's add a recursion to our tree node. So now the tree can output work records to itself, and we add a recursion depth limit of 5, and when we code that out, we can see how this recursion slowly generates a very simple tree. Now, people might know this tree. This is a very common example of an L system plant. So this is a very simple tree, but maybe a good start to learn about work graphs, and this is all the code you need to draw this tree. Now, we wanted more realistic trees, and for that we went back to a paper from '95 from Weber and Penn. And so how does it work? Basically, trees are designed as sets of parameters, so you have like an array of parameter sets, and these parameters define the shape of the tree. So you start with initial tree position and a tree type index, and maybe a random seed, and then the generation system generates transformations, and maybe another one, and then these transformations are connected connected by these rings, and the rings are connected by segments, which are like these cones. And this is still kind of boring, so the system or the paper also describes how to do splits. So this stem could split here, and then you would have just the same thing, but with a different initial transformation, or you could also split again. Now, if we label all these elements, this is something that is called one level. So you have the rings and the segments. And to make trees even more beautiful and a little more complicated, trees can have multiple of these as levels. So this is level 0, and then you could have at another level, and that does the same thing and has also a set of parameters. And as you can see on the left side here, trees can have up to 4 levels. Okay. So this can generate many, many different tree types, but how could we actually implement this with work graphs? So one thing we could do is say, now we can launch new work, and every time we split here, we just say, just relaunch. And every time we have a child, we also launch, so many, many launches. But this comes with a couple of problems. First of all, launching is not for free, even with work graphs. So that would be fairly slow. And also with like complicated trees, this would exceed the maximum depth of work graphs of 32. So this is not a solution for us. One thing we could do though is we say, okay, maybe one level we can do in one compute shader, but then for the rest we can relaunch. So now we have a node for level 0, and this level 0 outputs to level 1, level 2, and so on. So you have this chain of levels, and the thing we now have to figure out how to do to generate one level in one compute shader. And one thing we could do here is we employ a stack. So maybe you could say, okay, let's generate the trunk, and upon a split, we could say, maybe push that position to the stack, and then push again, and when we reach the end of a stem, we pop the stack, and this way we could generate a level. But this also comes with a couple of problems. First of all, this would be kind of unnecessarily complicated to manage the memory. Secondly, you could have high thread divergence when different threads generate different tree types, and the splitting behavior is different. And lastly, a thread cannot output this much within the work graph spec, so this is also not a solution for us. And the solution we came up with to generate a level is to launch a level as one wave. So you get like an entire group of 32 threads, and these 32 threads should cooperatively generate this level without using a stack. So this is how we launch it. And here I made a table about which thread computes what. And initially, there's not much going on there. All the threads are computing the same thing, the first transformation, and thus the first ring of the tree. Next up, we write a record for drawing that segment, fair enough, and for generating the 2 children of level 1 in this case. So there we have the first parallelization because thread 0 and 1 do something useful. And now, after the split, we split our wave into 2. So one half of the wave does one branch, and the second half of the wave does the second branch. And this way, we get more parallelization, and we continue this idea with writing the segment and for writing the children. And when I continue this for a whole tree, you can see in the end, most of the threads do some useful work. And this way, we prevent a thread, we prevent using a stack, and get a fairly fast implementation of one level. All right, so this concludes how we compute the levels. Let's talk about how we actually draw the trees. So we have a node that draws a stem segment. And for these, we want to do a couple of things. We only want to generate the tree parts that are within the frustum, obviously. We can say that we only want to generate a geometry that is within the frustum or within the shadow frustum, and everything else we can just discard. And you know that work graphs, or with work graphs, all of these launches are dynamic decisions, so we can just say, hey, is my child, whatever I would launch, is that outside of the frustum? If it is, then I just omit launching it. Okay, so for the second thing we want to do, we only want to generate everything that points towards the camera. So we want to prevent generation of back-facing triangles, essentially. And for that, we did an analysis and quickly realized, okay, basically a tree trunk is essentially a a tube. And for a tube, if you think naively about it, you only need to tessellate like halfway around it. So it's only the part that points towards the camera. And then we analyzed it a little bit more and found out, okay, with the change of radius, this also changes a little bit, and we derived a formula for that. And in here is also the relationship, so the dot product between the tree growth direction and the camera. And here you can see how these two relate. And with this, we were able to only generate the triangles that point towards the camera. And here you can see this in action. So we have two cameras, one static, one on the right, and on the left, one that rotates around the tree. And as you can see on the right side, when we basically go behind the other camera, we can see that only the triangles that are required for the green camera are generated. All right. So the last thing we want to do is we only want to generate in the quality required for the current frame. And for that, we employ tessellation. And for our stem segment, we have 3 tessellation factors, one from where the stem is growing from, one where it's growing to, and one for the length of the stem segment. And this delta here is just a user-defined sample distance. Basically, it says how many triangles should I have per pixel, or how many pixels should I have per triangle. All right, and here you can see this in action. So again, on the right side, we have a static camera. On the left side, we have the camera moving away from the tree. As we move away, you can see that the triangles collapse and disappear. And now we have reached a point where we can even remove some stems. Basically, we say if a stem is thinner than a pixel, we can probably omit it and do some kind of contribution culling. And as we reapproach our tree, you can see these stem segments generated again, and the number of triangles increases again. All right, so this concludes how we draw our stems. Next up, we want to make our trees a little bit more live and beautiful with leaves. And for leaves, we didn't really have a model, so we designed our own that runs in a mesh shader. And so we designed a couple of parameters for designers or for artists to design our leaves. And one trick we use for opacity mapping is from Loop-Lin for basically discarding all the fragments that are outside of a quadratic Bézier patch. And so you can see the example from font rendering, and here's our version for leaves. And this way we get opacity mapping. And we do something very similar for our needles, which are also fully procedural and run in a mesh shader. Yeah, and for level of detail, we use a common trick for leaf rendering. We just, when we move away from a tree, we increase the size of some of the leaves, and most of the other leaves decrease in size and disappear at some point. And this way, on average, the tree looks the same. And as we reapproach the tree now, you can see the leaves reappearing and getting more and more detail. And there we go. One more thing we can do with real-time generation is just to say, based on the current timestamp, we can maybe modify the generation a little bit to allow for animation. So here you can see we just use Perlin noise to offset the tree transformation a little bit based on the timestamp, and I think we could achieve fairly realistic-looking wind animation. So on the top right we have a slow breeze, and on the bottom right you can see a proper storm maybe. Another thing we can do with real-time generation is to have seasonal details. So here on the bottom right you have an indicator with the season, the current season, that we are right now in fall, and leaves start turning yellow, and now maybe brown, and start falling off slowly. And we have arrived in winter now, and snow starts falling onto the branches, and they start to bend down a little bit. And now we have arrived in spring, where blossoms start to grow from the branches, and grow and grow and grow. And slowly you will see some of the blossoms falling off, or all of the blossoms, and for some of them, fruits will be generated. And there we go. And you can see the apples growing there. And this is all stateless. This is all just based on this one floating point value that gets input into the generation. Next thing you can do with real-time generation is editing, as I mentioned. So here we change the tree parameters in real time, and an artist can essentially just edit an entire forest with just dragging a slider. Yeah, it's a good harvest this year. Yeah, and because one input of each tree is a random seed, each tree is also unique, so you can just change the seed if you don't like the current tree. Another thing we implemented is we wanted more control for the actual spline that gets generated, so we added some functionality to like bias it on the left here, where we basically could design archways and stuff with it. And on the right side, we added a functionality to like prune the trees a little bit to like prevent them from growing into walls and whatnot. And this uses hardware accelerated ray tracing, similar to what we did last year with the dependent generation. All right, so for our performance evaluation of the whole system, we wanted to have a proper test scene, and so we built one using about 2,000 trees and bushes. You can see some example videos here. And this is actually based on a park, which is very close to this venue here. So you can take a break and go there maybe and like judge how good of a job we did. So based on this camera path I just showed you, we did our performance timing. So the x-axis is just along the camera path, and the y-axis is the render time milliseconds. And for just the G-buffer, so like generating the trees and rendering to a G-buffer, we need about 5 milliseconds, or a little less. And for rendering also to a shadow map and to a G-buffer, we need a little bit of more time, like 5.5 milliseconds on average maybe. And then for frame-to-frame times, we need a little bit more, maybe 8 milliseconds. And these measurements include the time for like temporal ambient occlusion, screen space reflections, and so on. And what's also nice here is that here the gray line is the number of triangles we generated, and it very nicely correlates with the performance. So we can say, hey, when more triangles are generated, our rendering is slow. So that's a good sign. One more thing we can do here, we can add a slider for the level of detail. So here we have a slider and we decrease it slowly. And because the level of detail is continuous, you can barely see anything changing. In fact, I added a visualization so you can actually see that something is happening. So here you can see the triangles disappear. And with this functionality, you can say, hey, my frame rate is kind of low right now. It's like below my target. Maybe decrease the level of detail just a little bit. So we reach our frame time target. And that's what we do with our timings here. So we said, okay, we have a frame rate target of 120 hertz. And sometimes we are slower than that. And as you can see here with the dashed line, for most scenarios, this regulation or this system is able to prevent these performance peaks. Okay, one more thing. I mentioned earlier that we wanted to do a little bit of compression, and we did an estimation of what our trees would, how much memory they would require if we would write them to memory, and we came to a number of 34.8 gigabytes, so that wouldn't even fit in our GPU VRAM, and our system needs, for just the tree positions and so on, only needs 51 gigabytes for rendering the whole scene, except for like the external assets. All right, so I presented a system for generating trees in real time. It supports cult generation, animation, continuous level of detail, real-time editing, seasons, automatic level of detail. And if you want to learn more about work graphs, feel free to check out our work graph playground. And if you want to play around with our tree generation, we have a sample in our playground where you can like change the parameters and so on. So go check it out. Thank you for your attention.
Do we have questions? Let me see. All right, I'll start with one of mine. Actually, I have many. One, you're showing here shadows, which is very wise. We like shadows. Does this imply that we need to perform some sort of like write to memory in order to like?
We generate, so basically for the generation, we generate everything that is either in the normal camera or in the shadow map camera. It's a little bit more complicated, and we basically launch two mesh nodes, one mesh node for the shadow map and one mesh node for the G buffer. So we generate once.
Very cool. Okay.
Great talk, Bastian. So did I get it right? You're essentially linear in the number of light sources. So you need to regenerate for every light source for the shadow map, essentially, right?
No, we don't need to regenerate once, and then for every light source we would launch a mesh node.
Yes.
Yeah.
So you get extreme memory savings, right? But you also pay the price per light, essentially. Is there something in between where you can potentially reuse stuff?
No, maybe to clarify, some of the trees are not generated in the mesh nodes, some of them are, so to say, the topology are compute shaders, and only the tessellation happens in the mesh shaders, or in the mesh nodes. So you would tessellate for each light source, but everything before that happens once. Okay? Good.
Thank you.
There's
Okay.
Oh, great presentation. Question about the rendering of the leaves. Do you separate the obviously opaque parts from the bits which are close to the edges so that you can decrease the number of places where you've got to do pixel discard sort of things? Because that would help potentially with depth buffer optimizations.
Yeah, we have only, we separate. Do you mean do we have two different mesh nodes or two different pipelines, or maybe could you elaborate?
I kind of mean, can with your leaf model, can you say this part here is a very simple polygon which is definitely opaque?
Okay, I get it.
And these bits are the bits where I have to do complicated
We don't
testing.
do so, but it would be no problem to do that, actually. Yeah, it's a good idea.
I think we have time for one last question. Okay.
Can you do occlusion culling as well? Occlusion culling?
Yes, the thing is, trees are absolutely horrible occluders. We tried that, it didn't help at all, it made it slower. Because if you think about it, if there's one pixel peeking through the leaves, we are lost. So
how about aggressive occlusion culling? You have a contribution culling already.
Yeah, it could work, yeah. But we don't do it.
Okay, this was fast. Maybe I can get one more. Okay.
Hi. Can you perhaps elaborate a bit how you would use this in a full-fledged system or a game? What about physics, preventing from walking into the tree, sound, and the obvious elephant in the room, ray tracing?
Yeah, I got a similar question last year, and then I said the techie answer is to just say collision you also do on the GPU. Come on. But you could, for example, in a game engine, you could say, what you still have to do, you could automate it, obviously, or could make it part of the work graph, is placing the trees. So right now, we have, in our testing, we have just empties, transformations with a random seed attribute and a tree type attribute. And for example, for a game, you could say, I will also generate maybe a dummy topology for the trunk, so the players cannot walk into the trees, but everything else, we don't really care if maybe a player walks through the tiniest branch, that's fine. So you could, in a game engine, you could say, okay, if there's empty, so the GPU knows where to generate the tree and what tree, and for the collision, you could just have a dummy object. Does that answer your question?
Cool. Let's thank our speaker and